So, we will start our discussions on the content of week 3. So, I am Adyasha Sahoo, a PhD student from the Department of Electrical Engineering, IIT Roorkee. So, I hope you have gone through the lectures of week 3. So, they were mostly on the energy storage devices. So, we'll briefly discuss the key concepts and see some multiple choice questions thereafter. So, firstly, we'll discuss why we need to integrate these energy storage devices to our system. So, firstly, as we know that the addition of the intermittent renewable sources, is making the load demand and supply balance a very difficult task for the system operators. Is adding uncertainty to the system operations. So, to manage these uncertain renewable energy sources and to integrate more and more such intermittent resources to our grid, the energy storage integration is a crucial, because what the energy storage system they can do is they can charge during excess renewables so that the grid is not facing issues of over voltage or over frequency, and then during the hours of their absence they can discharge. Thus they can help in managing the system operations. So the points that we discuss here, first is the grid stability and reliability. So by mitigating issues of over voltage, under voltage, frequency related issues, and also by helping in providing reactive power with the help of inverters. So they can also provide black start services. So by providing this range of services, they can help in the grid stability and reliability. Then integration of renewable energy, that as we discussed, that it can facilitate the integration of the renewable energy sources by handling their intermittencies. Then peak load management. So what the storage can do is basically this we have seen previously also. So during the hours of peak load, what can the storage do? Should it charge or discharge? So whenever the energy storage, let's say this is the grid and here is your load, and then you have a storage here. So charging means it will take power from the grid or consume power. So basically it will act as a load. And when the storage will discharge, or its discharging process means it will inject power to the grid. Inject power, so it will act as your generation or source. So during the hours of peak load, if the storage will charge, that means it will add to the load demand, means it will increase the load, which we don't want. We want that it should help to supply the power, that is, it should inject the power to basically supply power to the peak demand. So here during this time it should discharge during the hours of peak load, and during off peak load hours it can charge. Okay. Then next is frequency regulation and voltage support. So the frequency regulation is similar to yes. So the frequency regulation is similar to the active power balance. Basically, whenever for frequency regulation, that is FR, whenever there is over frequency, over frequency implies the frequency is greater than your nominal, which is 50 hertz. That means during that time, your generation is greater than the demand. So the storage should basically, yes, when there is excess generation available, the storage can charge, and during periods of under frequency, when the frequency is less than 50 hertz, means your there is less generation than the demand, then during these times the storage can discharge, so that the generation and demand is balanced. And whenever the generation and demand is balanced, then automatically it will reflect in your frequency, so that your frequency is at 50 hertz. So that is frequency regulation. Then coming to voltage support, so the storage inherently cannot provide voltage support, because for voltage support what you require is reactive power. So for providing voltage support, you need reactive power support basically. And that is not provided by the battery, but the battery energy storage system is usually integrated with the inverter, and this inverter can provide the reactive power support, and hence they can help in the voltage support. So basically whenever there is over voltage, for voltage support, whenever there is over voltages, so we can absorb the excess reactive power, and whenever there is under voltage we can inject the Q or reactive power to basically regulate the voltage. Then next is grid resilience and black start. So during any severe fault, what may happen is there may be complete outage of the system. So for black start, the crucial thing that we require is either black start generators, which do not require any startup power. So these storage devices, since they also do not require any startup power, they can help in the black start restoration of the grid. So since for black start support, the energy storage device do not require startup power, so they can facilitate in the system restoration also. Then time shifting. So this we will see in the next slide. There is no space here. Then deferral of grid infrastructure. So, what will happen is basically, let's say, this we'll see in the next slide. There is no space here. And electrification of transport. So basically, the energy storage, as the technology is advancing, so they are crucial for the electric vehicles, since there we have a portable storage device installed in the EVs, and then whenever we can charge and discharge them for the electrification of the transportation sector. So hence their technology is crucial for the electrification of our transportation sector. So here we have 2 points left with us, time shifting and deferral of grid infrastructure. We'll see it in the next slide. Then here some applications are discussed. So the key regions where large scale batteries, I think the slide is not moving. Yes. So the key regions where some large scale batteries have been installed are basically Australia, China, Germany, Italy, and United Kingdom and United States. And the global installed capacity of the large scale battery energy storage system was about 10 gigawatts, and this data is up to the year 2017. And what services they are providing? So, various ancillary services such as frequency and voltage, then capacity reserve also, then a renewable energy capacity firming and curtailment reduction, reliable power to isolated grids. So, whenever we don't have the grid connected system, that is, we are having the islanded system or isolated system. So, there the installation of storage is a must to handle the intermittencies, because there you don't have the grid support with you. So, hence, for the smooth operation of the islanded microgrids or grids, the installation of the energy storage system is a must. Then deferral of transmission and distribution upgrades. So this is basically infrastructure deferral. So saw that they help in peak load management and also addition of RES. So with this applications, what they can do is we can defer the investment, additional investment in generation expansion, that is addition of new generators to the system, or deferral of investment in the transmission and distribution lines, that is a network expansion, transformers, substations, basically all those things. So they can be avoided or they can be minimized with the addition of the storage devices. So currently we see that the lithium ion batteries are quite popular, and they are covering about 90% of the total capacity that has been installed for the large scale battery storage projects. And the cost, the technology is improving, and 80% reduction in their cost has been observed in 7 years. And the largest capacity project till date are the battery installed at California of ratings 300 megawatt and 182 megawatts respectively. And some popular manufacturers are here. Then another application-based batteries we will see here. Basically, the battery installed by Tesla of 100 megawatt capacity at South Australia, which is providing frequency regulation and capacity firming. similarly at Germany for frequency regulation, at Italy for grid investment deferral and reduced renewable curtailment, then at Japan for these ancillary service and renewable curtailment, and similarly at Micronesia for the this is for basically your islanded grids. Because the whenever you don't have renewables, what used to happen earlier in this mini grids is we use diesel generators to supply the load. But now what we can do, we can store the excess power that is with us and then discharge whenever the renewables are absent instead of using diesel generators. And hence, by this way, we the dependency on these diesel generators will be decreased. Then some other datas for that how they have resulted in savings for the grid operators across the world that has been discussed here, and reduction of fossil fuel usages, reduction in frequency response cost, and other things. So these are showing that the potential impact of energy storage and power sector transformation by reducing the cost of new investment, by reducing the cost of ancillary services, and also by integrating more capacity of renewables to the grid. Then next, we see here basically this is what we call the duck curve, and how the energy storage is helping us in flattening this load curve. So you can see that as the years are passing here, so what first we'll see what is the problem with this duck curve. So you can see from this region what is happening. There is a sudden decrease in the load demand. So that means here during this period, you need ramp down services. That is, suddenly you need your generators to go from, let's say, 100 megawatt to 20 megawatt. And such a rapid decrease in the capacity is usually not possible for the fossil fuel generators. And similarly, during these instant, what is happening again? So there is a sudden requirement for ramp up services. So what the storage can do is it can basically, whenever there is a need for ramp down services. So ramp down services means you need to decrease the generation, basically decrease PG. So decrease in PG means the storage can energy storage can provide these ramp down services instead of this decrease in the PG. So energy storage can provide this service by, oh, how to explain basically. Similarly, for a ramp up, you need to increase the generation, or what you can do, the second alternative is to decrease the load. Similarly, for ramp up, you can either decrease the generation or increase the load. Or the third alternative that we have with energy storage is that instead of generation and demand, the energy storage can also help here by charging here, and here it can discharge. So we saw that as the years you can see from 2012 to 2016, this duck curve was basically the duck curve. The dip in the generation and then dip increase in the generation. It was rapidly moving down, but with the help of energy storage, this blue line, so we were able to shift this duck curve above in these periods and bring the reduction during these time, so helping in flattening the load duck curve. Then here are some data that how the lithium ion is capturing the energy storage market. So we discussed that about 90% of the installed capacity is by the lithium ion. So you can see here in 2016 about 1.62 gigawatt of lithium ion battery has been installed, and some amount of sodium sulfur batteries are there, and then other technologies are here. The next here we discuss are the characteristics of the energy storage. So basically, the two characteristics are the energy density of a storage and the power density. So basically, in energy density, we see that how much amount of energy can be stored, that is energy per volume or per mass. So hence, it is like your energy is in watt hour. So watt hour per meter cube or watt hour per kg. So higher the energy density means the higher amount of energy can be stored by the energy storage system for a given volume or mass. So lithium ion batteries are basically high energy density type of energy storage, and hence they can provide compact solution. That means smaller weights of battery or smaller volumes of battery can store more amount of charge, and hence for that they are popular for electric vehicles, because in the vehicles the weight of the battery is important. So instead of using bulkier batteries, we can use lithium ions. They are more compact and hence they have less weight, but they can store more amount of energy, and hence they are having increased applications in this EVs and also in electronic devices, portable electronic devices. The next thing is your power density. Similarly, power density is basically the rate of change of energy. It is the rate at which energy is delivered or stored. So here it is unit is in watt per meter cube or watt per kg. So this implies that for a given uh, time, basically time frame, which technology can charge at a faster rate and which can discharge at a faster rate or slower rate, basically. So when we say that our storage is having high power density, means it has a capability of charging very quickly in the matter of minutes, and similarly discharge also rapidly in the matter of minutes. So for that, we require, and depending upon the application, basically, you can choose a high energy density device or a high power density device. And supercapacitors are the best example. So there is a trade-off between the energy density and the power density. So because one storage technology cannot have both the characteristics due to its chemistry and all. So for that, that batteries, basically the storage technologies which have higher energy density usually have lower power density, And the batteries are a example of your high energy density device, high energy density but low power density. That means they can store the energy effectively for longer duration and in a more compact volume, but they cannot charge in a matter of minutes or discharge similarly. But the supercapacitors, they have high power density. That means they can inject power or they can absorb the power very quickly in the matter of minutes, but they have low energy density. That is, they cannot store this for longer duration or in compact forms. So that is because inherently of their technology that they use. So in battery, we have chemical reactions going inside them, due to which these chemical reactions cannot take place instantly in a matter of minutes, and hence they are having low power density. But supercapacitors are working on the principle of electrostatic, and hence they can basically charge or discharge quickly, giving you high power density. So depending upon the application, you need to choose whether you want to install a high power device, a high power density energy storage technology, or a high energy density storage technology. So if you want to basically have a portable kind of application like EVs, then you use a high energy density. But let's say you want to provide grid services such as frequency regulation. So frequency regulation, so the time scale of operation is in minutes. So there you need high power density energy storage technology. So if you divide it in the time scale range, so for minute range, we have high power application, high power density energy storage. For longer durations, we have high energy density applications. And furthermore, if you want to store for longer, let's say days together, days or months, then we have days. The storage technology that we generally use earlier was pumped hydro storage. So pumped hydro, we know that whenever there was excess rainfall during the rainy season, so we store the excess water in a dam or reservoir, and whenever the monsoon season has been passed and we have summer, then the reservoir water is used to basically drive the hydro power plant and supply electricity. So hence it is a kind of seasonal storage. You store it for very long hours. So earlier it was pumped hydro storage. Now the other popular kind of storage is your hydrogen storage or green hydrogen storage. So green hydrogen storage in the form of ammonia. So what you do, you basically store using fuel cells. Basically, first you dissociate the water and then you convert it into ammonia and store it in ammonia tanks for longer duration, and when you need electricity you can convert this ammonia back to electricity with the help of fuel cell. So for longer duration this ammonia storage is now getting popular. Then next thing is energy shifting versus peak shaving. So energy shifting or load shifting is basically whenever there is periods of low demand or low price, then during that times you basically charge. So whenever there is low price or low demand, so you can charge the energy storage, and that stored energy you can discharge during periods of high price or high demand. You can discharge the same energy. So that way, basically, we avoid the higher energy cost during the peak hours and we maximize the use of renewable energy sources. And what happens in peak shaving is basically we try to reduce the peak power demand on the grid during the periods of high electricity consumption. So during high demand or peak demand, the storage can discharge to provide the power to the peak demand of the system, and that is the peak shaving. So the main focus of the energy shifting is basically we exploit the prices that is going on in the system, and also we see the renewable profile that we are getting over the day, so that we can basically optimize our energy consumption throughout the day. So basically what is happening here, that let's say you want 10 kilowatt hour of energy you want to consume over 24 hours, but which intervals you will take this power, so that we optimize using the energy shifting application. Then in peak shaving, basically we want that the peak demand on the grid is reduced, or basically the price will be also reduced, and hence the grid will be relieved from the stress. So hence, what strategy you want to apply, basically apply, that will depend upon various factors such as the what is the pricing structure of the grid that we are in part of, the demand profile, the available energy resources, the profile of the renewable energy, and those all will basically if, impact what strategy you want to use. The next, these energy storage devices, they are subjected to the process of aging. So there are two types of aging that take place for the storage devices. First is the calendar aging. So calendar aging means that even if you do not use the device, then also there is a decrease in its capacity with passage of time. So such decrease in its capacity, even if you keep the storage idle for certain instant, so that is referred to the calendar aging. That is because even if the battery is idle, so the chemicals that are present inside the battery, they will be going some slow chemical reactions throughout their lifetime. And due to this, basically, there may be decrease in its capacity as it is aging. And these factors, various factors that impact the calendar aging are basically temperature, because we know that there are some reactions where temperature will act as a catalyst. Means at higher temperature, the chemical reactions will be faster, and hence they will facilitate in the faster aging of the storage. Then state of charge. So basically, keeping the battery at higher SOCs, at extreme higher SOCs, will also accelerate the aging of the energy storage. And lastly, this chemical reactions that I said, that whenever you are, even if you are not using the battery, these chemical reactions are always going place, because you know that there will be some metal corrosion and all, due to which there will be degradation of the battery. So uh, yes, Vijendra Singh sir, I think you have raised your hand. Do you have any question? Then the next type of aging is your cycle aging. So cycle aging will depend upon how you are using the battery. So it will depend upon the charging and discharging rates, how frequently you are charging the battery, at what rate you are discharging or charging the battery. So these all attributes will affect the cycle aging of the battery. So because every time you basically you are charging, that means you are some chemical reactions are taking place. When you are discharging, that same reversible reaction is taking place in the other direction. So that leads to some irreplaceable capacity loss. And over time, these losses they will add up, and hence there will be a reduced capacity or the decrease in its performance. So basically, the factors that affect the cycle aging are basically higher DODs or depth of discharge. So greater the depth of discharge, generally faster the cycle aging. Similarly, charging rates, the faster the charging rate, similarly, there will be increase in the cycle aging of the batteries. Similarly, charging and discharging protocols. So each battery they will be having some manuals, some protocols that how to handle these batteries. So if you do not stick to the rules that are in the protocols, then they can also accelerate the aging of the batteries. Let's say so here, if we see compare the both type of aging, then for to reduce the calendar aging, we need to keep the batteries at a moderate temperature. So for that, if you see the battery containers, so how these batteries are installed is basically, let's say you want to install a 100 kilowatt hour battery. So that doesn't mean that you will have a single battery of 100 kilowatt hour capacity. Rather, there will be combination of cells in series and parallel, and they will be connected in such a way that the total output or the total capacity will be 100 kilowatt hour. And this arrangement will be in racks. There will be basically arranged in rows and columns, and there will be a structure. And then they will be kept inside a big container type of thing. And that container will be having other things such as the battery management system. Then there will be the power converters, maybe also inside that container. Uh, Power converters, battery management system, the batteries. There may be some monitor also to monitor continuously monitor the health of the battery. Then the whole container is basically always there are some kind of cooling systems. There may be ACs or HVAC type of coolings, so that the temperature at which the battery are there, they are moderated so that they don't get heated up, so that they can the lifetime is basically increased in such a way, because heating will basically lead to faster calendar aging. So to avoid that, they are stored in a cool place generally. Then, to reduce the cycle aging, what we need to do is we need to monitor that the number of charging and discharging cycles it is undergoing in a day. So you need to monitor that and not very frequently charge or discharge these batteries to basically overall mitigate the cycle aging. And also we need to other to the stick to the protocols that are provided by the manufacturer, The we should maintain the charging rates, the discharging rates, the number of charging cycles, the number of discharging cycles, the temperature, and everything else. Whatever is in the manual of the manufacturer, we should stick to that to avoid the cycle aging. And next, we see the capability curve for a battery. So similar capability curve we have also seen for synchronous machines, right? So can you point out what is the difference between the capability curve that you see for a battery and the capability curve of the synchronous machine, synchronous generators that we have studied earlier? So here you can see there are in the x-axis you have the active power in per unit, and in the y-axis you have the reactive power. So the y- you can see the four quadrants have been covered here. That means the active power is both positive and negative. So positive will imply injection or basically discharging of the battery, and negative will mean the charging of the battery. Similarly, the reactive power is also in the positive y-axis and also in the negative y-axis. Hence, here we see that the capability is curve is covering all the four quadrants. But for the synchronous generators that we study, if the P is in the x-axis and Q is in the y-axis, so there the generator can only inject power, it cannot consume power. So the capability curve is something like this. The reactive power it can inject or absorb, but the active power it can only inject. So that's why we get a half semicircle where only the first and fourth quadrant are covered. But for the battery, we have the four quadrant operation here. So you can see here the uh, rated, basically it is in per unit. So it is varying from 1 per unit in the positive side, that is in the injection side, and -1 means in the absorption side, it is also going to the 1 per unit. Other thing that we can observe is basically this gives us the uh, basically this circle equation is given by p square plus q square is greater than equal or less than equal the s square. So as the active power capability, is increasing in this direction, so as the P is increasing, P gen, we say that the Q gen capacity will decrease. And similarly in this direction, as the Q gen capability is increasing, the P gen capability is decreased because of this equation. So here you see there is a red line and some blue dots are there over the line. That means we are considering the operation of the battery along this red line only. So what is this red line implying? So here you can see the slope is basically fixed. So that slope is nothing but the power factor. So basically we are operating the battery at in the constant power factor mode. So this red line is the constant power factor mode line, and the blue points are basically various operating points that is acceptable for the constant power factor mode. Similarly, if you see the red line here, so it is the constant Q line, right? So somewhat around zero point 0.4. So here, whatever be the active power, the reactive power is being fixed at zero point 0.4. So hence this is the operating mode that we are considered is the constant Q mode. and blue dots are the acceptable operating points for such a mode. Then we have the general model of a energy storage system. So here basically you have the grid. This is the grid. Then you have the inverter, which is converting this AC to DC. Then this idling loss is basically that we discussed is somewhat similar to the calendar aging. That means even if you are not using the battery, there will be some loss in its capacity, some loss in its energy. So that is represented by this idling losses. Then the state means what is the state of the battery, whether it is charging, whether it is discharging, or it is in idle mode. Similarly, the next thing that we represent here is the charging and discharging losses. So basically, what it signifies that if you charged, let's say, the battery to 1 kWh, but the amount of energy that you can extract will not be 1 kWh. It will depend upon the efficiency of the battery. Maybe zero point 0.9 kWh of energy you can derive from the battery if you charged it by 1 kWh. So that is represented by the charging and discharging losses. And this is the stored energy or the idle storage. So the idle storage with the various losses of charging, discharging, and idling losses, that will give the practical energy storage model. So if we see the equation here, so the energy stored at time t and time t plus 1, they are related by this equation. Then this next equation that you see is u. So u is nothing but the binary variable. So a binary variable can take only 0 or 1 values, right? So there are two binary variables, u charging and u discharging. So we know that for a given time instant, the battery can either charge or discharge. So to mathematically model it, we model it using this equation. Also, this equation is saying that the sum of U discharging plus U charging should be less than equal ones. So what are the acceptable values of U charging and discharging then? If U charging and U discharging at 0, 0, that means the battery is in idle state. If it is 0, 1, that means the battery is in discharging mode. And 0 plus 1 is basically 1. So this constraint is, this equation is satisfied. And previously 0 plus 0 is 0 and 0 is less than equal 1. So this condition is again satisfied. And if 1 and 0, then the battery is in charging mode. Again 1 plus 0 is 1. This equation is satisfied. But if both are 1, then their sum 1 plus 1 is 2 and 2 less than equal to 1. That means that equation is not satisfied. So this is not possible. So that way we can model it through this equation. Then some other condition that uh, what was at, let's say at t equal to 1 for 24-hour period, what was the energy storage energy that was initially available in the battery, that is represented by E11. And let's say at the end of the day, at t equal to 24, you want that the E124 is, let's say you want it should be 50% of the rated capacity. So then throughout the day, the charging and discharging can be done in such a way that at the end of the day, at T24, the SOC of the battery is at 50% of its rated capacity. And this is the formula of depth of discharge, which is 1 minus the energy at time t by the rated capacity. Then next, here we discuss that uh, how to basically formulate the objective and the constraints to basically have a optimization problem to solve the optimal sizing and setting of a energy storage. So first of all, why optimal sizing and setting is required? Can you say, Rajesh or Akhtar, anyone, why optimal sizing and setting of energy storage system is required? So basically, these storage devices, they are not cheap devices. So their installation requires huge amount of money in crores maybe for some kilowatt hour of capacity. So we cannot install them uh, at every location, right? So let's say there is a 30 bus system. So you cannot install the energy storage at all 30 buses of the system. Firstly, such a capacity is not required, and also, secondly, such amount of money is not with us. Maybe for the 30 bus system, installation of one or two energy storage system is sufficient. So let's say for the 30 bus system, we want to install two energy storage devices. The next question that comes is where to install these two energy storage systems at bus 1, bus 2, bus 1 or bus 4, or which two locations are the most ideal location depending upon our need. So let's say we want to minimize the system operation cost or minimize the installation cost or minimize the frequency regulation cost or we want to minimize the emission. Depending upon our need, which location is the best ideal, that we need to find out, and that can be done with the help of a optimization model. So for one optimization model, its structure is such that optimization problem will have a objective function. So the objective function is nothing but what you want, what is your motive, whether it is cost minimization or profit maximization or emission minimization. So these are some examples of your objective functions. The next thing that is constraints. So constraints are nothing but the uh, equations which model the physical characteristics of the system. So constraints which will model the power flow through the lines, power flow equations. Then there will be constraints with respect to your technical capability of various resources such as generators, because you know the generators can generate only within their maximum rated capacity. Similarly, technical capability of the energy storage, like the charging and discharging constraint that we saw. Then there will be constraints on the voltage of the system. So the voltage must lie within a certain band. That is basically we try to keep it between zero point 0.9 per unit to 1.1 per unit. Similarly, there will be constraints for frequency of the system. So we want that the frequency of the system lies between 49.5 to 50.5. Then there may be constraints for reserve. So reserve we keep for in the case of contingency or faults, then these reserves can be utilized. So there may be constraints for that. Then there may be constraints for thermal limit of the transmission line. That is, the power flowing in the transmission line should not exceed its rated thermal capacity and all these. So these are some of the examples of constraints that we see. So here you see the first step is to identify the application to be served, to be provided by the energy system. That means what you want to do with the energy storage system, whether it is the time shifting application, whether it is a peak shaving application, whether it is you want to minimize only the installation cost, or what is basically you want, or whether you want to maximize the life cycle of the battery, whether you want to minimize the emissions of the system. So these all are some of the objective, and you need to first identify that what you want. And secondly, formulate the optimal size and location of the energy system, satisfying the various technical and economical constraints that I said here, right? So here you see some example of objective are given, such as minimize the investment and operation cost, or minimize the losses in the system, minimize the voltage deviation. Then constraints are power flow constraints, energy storage operation constraint, and upper and lower bounds on decision variables. So this is nothing but the upper and lower bounds on the voltage, frequency, active power generated by the generators, by the renewable energy sources, the bounds on the power flow through the lines, so those all. Then, when this problem has been formed, then next we see how to solve this problem, or that we say is the method to solve the problem. So this problem we can solve using classical optimization techniques. You can use heuristic algorithms, or nowadays you can use ML or AI based algorithms to basically solve this above optimization problem. Then basically this will give you the final result. And in the result, what you will get the location. Let's say the location, it is saying that at bus 7 and 24, you need to install the energy storage, as well as it will give you the size. Let's say the sizes are somewhat like 50 kilowatt hour and 150 kilowatt hour respectively. So that will use your solution. So you give the you frame the optimization problem, you solve it using certain technique, and you finally get your solution. After you get the solution, you again validate the solution and test it on the network. Means now what you will do, you're using some simulation studies, you will now basically connect a 50 kilowatt hour battery at bus 7, connect a 150 kilowatt hour battery at 24 bus, and then you see that how the system is reacting, whether the stability is there in the system or any other issues are arising. So after that, we need to cross-validate whether the system is working fine. And when the system, if the system is working fine, that is the validation has been done, then we go for the installation of the battery in the actual test, in the actual network. So here some examples are given. So power flow constraints. So this you have seen earlier, right? That the power flow between bus Pij, that is given by Vi, Vj, I think Gij cos delta I minus delta J minus theta Ej. So something like that, right? So those are your power flow constraints. Then similarly, power loss constraints are there, which is the P loss is generally given by G theta square, theta Ij square. curtailment constraint, energy storage constraints and capability constraint, and reverse power flow constraints. Similarly, from economic point of view, the investment constraint, the operation maintenance cost, load curtailment cost, budget limitation cost. Because let's say you have $500 with you, and you want that the installation cost should be less than the your budget. So that also need to be ensured. Then arbitrage benefit. Basically, arbitrage means when you basically exploit the difference in prices. Whenever there is low prices, then during the interval of low prices, you can charge the battery, and during interval of high prices, you can discharge the battery to earn more profit. So arbitrage is nothing but profits obtained by exploiting difference in grid prices. Then next is your environmental parameters, that is your emission levels, resiliency, land availability. That is also a constraint because these containers, as I said, the arrangement are kept in huge containers, and that much amount of land also you must have with you for installation. Then battery disposal and recycling. So after, let's say, the battery has the age of 25 years or something, so it will be degraded. So after that, how to dispose this battery or to recycle this battery? Then we can also consider the degradation of the battery. So all those parameters can be considered. Then coming to the methods that we use. Yes. So there are four types of methods that can be used. First is the analytical methods. So that means direct calculations, but that we can not do for large systems. And obviously, it will be having slow convergence and the accuracy will be also low. Then next is the mathematical optimization approach. That means that comes under the classical optimization techniques. So that will always give you optimal solutions, and for linear problem, at least it will always give you the global optimal solution. For non-linear problems, there are some concerns that we'll see. But again, for larger systems, these techniques may face issues of convergence for non-linear type of problems. Then use of artificial intelligence or machine learning techniques. So they give very fast result even for larger test systems. But here the optimality is not guaranteed for such system. And also to train these models, you need a large amount of historical data with you. Then next is the meta-heuristic approach, such as your, popular techniques such as GA, PSO. Again, these techniques, they always give different solutions for different runs of the same algorithm. So these are also not robust in the solution point of view, but their implementation is easy. The next thing is the that we require is the battery management system. The battery management system is basically installed near to the maybe where the battery is installed or in a control room, and its function is basically to look after the overall operation health of the battery. So it undergoes functions such as cell balancing that we will see in the next slide, Then thermal and safety management. Basically, it will monitor the temperature inside the container. And if the temperature is very high, it may give you alarms to you so that you know overheating is taking place and you can then basically switch off the battery and look for its safety. Then it can help in the optimal performance because in the battery management system, you can enter basically how many times you want to charge, discharge. You can give commands through this battery management system to follow the protocols that are being given by the manufacturer, and that way you can have the optimal performance. Then data logging and reporting. So basically, it there is also monitoring system which at every instant looks after the various attributes of the battery. So you have a report with you. Even if something is wrong, then you can go through the report and see that what went wrong and analyze accordingly to avoid those situations in the future. Then communication systems are you can also install within that battery so that you can communicate with other uh, batteries for to basically coordinate their charging and discharging, such as you know that this network you can form a network connection. Basically, this is the area one, this is area two. You have here a base installed, base one, base two, so they can connect here either through wired or wireless, depending upon their distance. Communication to optimize the operation in both the areas. So they can be coordinated to optimize the overall performance of system. Then is enhancing lifespan. Obviously, when you basically look or you have temperature monitoring, SOC monitoring, then also rate of charging and discharging. Those all things you can do with the battery management system, and these all things will ultimately enhance the lifespan of the battery. And lastly, state monitoring and control. Basically, the same thing only. You monitor the state of the battery, whether something is wrong. If something is wrong, you can give the control actions to rectify those mistakes, or you can send alarm messages to the operators so that they can take the actions. Then the next thing is cell balancing. So as we were discussing, no, that when you have a battery of some capacity, so that capacity is achieved by the series and parallel connection of the batteries. So there will be many cells, a set of cells, then they will be connected in some series parallel connection, and together they will give you that amount of capacity. So when you have a number of cells that are connected, so each cell should have the same SOC level. If they are having different SOC levels, then there will be they can hamper the system operation. How? Let's say you have two cells. One is at let's say 10% SOC, one is at 50% SOC, and you give a command to the battery to discharge. So what will happen is the 10% SOC battery will be going to greater depth of discharge, which can hamper its operation. And similarly for the higher SOC also. So for that, what we need that each cell SOC should be same within that overall battery connection. And firstly, why this difference in SOC comes is before you even start the battery, let's say a new battery you bought from the manufacturer, you have installed it within your microgrid or your location. Then when you start the battery, Before that, you need to ensure that all the cells are balanced so that you can have the efficient operation. So due to difference in their chemistries and all, so initially they can have different SOCs. So for that, we need to balance the SOC of these cells first. So this safety compliance as we discussed. So safety concerns that as we discussed and enhancing the overall system of performance. Then if they have uniform SOCs, then obviously they will have uniform charge and discharge rates and size SOCs. They can also help in the voltage stability because no cell will drive towards under voltage or over voltage. They will be having the same voltages across them. Enhance safety, again, the same thing that it will ensure that no battery is going to very low depth of discharge or very high SOCs. Then obviously maximizing the battery lifespan, capacity optimization, and energy efficiency. These all can be achieved with the help of cell balancing. Then to achieve this cell balancing, we have basically two methods. One is the passive cell balancing, other is the active cell balancing. So what happens in passive cell balancing is what we use is let's say there are two, three cells. So the cell which is having the highest SOC, so we try to discharge it and bring it to the voltage level of the cell which are having lower SOC. So let's say there are two batteries of 50% and 60%. So we will discharge the cell which is having 60% SOC to 50% SOC so that both the cells have the same SOC. So that we do with the help by discharging the higher SOC battery through external resistors or by by connecting a external resistor across the higher SOC battery and discharging it. So here its advantage is it is basically simple. You don't need higher efficient devices for it. Only a resistor is enough for it. You don't need additional components such as switches or other devices. But the disadvantage here, it is a slow process because you are basically dissipating the energy in the form of heat. So it is a slower process. It will take time. Then it is not highly efficient because you are wasting the energy in the form of heat here. So the overall efficiency is decreasing and limited balancing. That means let's say a cell is at 90%, other is at 30%. So to discharge the 90% battery SOC to 30%, so that much amount of difference cannot be handled with the passive cell balancing. Even it can be handled, I think it will take very much high amount of time. So when the difference between the cell SOC is very large, this process is not effective. So the application here that we use is it is very simple. So whenever the cell SOCs are not varying largely, so that and when the time is not a constraint for you, so during those application you can use passive cell balancing because they are simple and cost effective. Then the next approach that we do is the active cell balancing. So in active cell balancing, we again here try to equalize the SOC levels of the battery. Yes. So there, what we do, the energy is transferred between cell to cell transfer. Energy is transferred. That's why it is basically energy higher efficiency is there because here the energy is not being dissipated in the form of heat and also it can happen very quickly. It is a faster process and it can also handle the balancing when the SOCs of the batteries are varying by a large difference. But the difference is here you need complex electronic circuits and switches, adding to the cost. So, its application is whenever you want to rapidly, basically quickly balance the cells, and also if the cell have a higher difference between their SOCs. So, for such application, active balancing is preferred. So, if you see here, uh, the technical requirements for the addition of the energy storage, we require software such as battery management system for protecting the batteries, for the management of operation of the battery. Then we also need policies because, as I said, a huge amount of cost is required. So subsidies and incentives from the government can help in uh, adding these resources to the system. Then wholesale market. So basically, we can allow this battery energy storage system to provide various services, such as we discussed frequency regulation, voltage support, and black start. So by allowing them to participate in market, we are allowing them to basically have higher profits, and these profits will attract the investors to install the battery energy storage system in the grids. Then a transmission and distribution system that we saw that it can facilitate in system operation by peak shaving, time shifting, frequency service, voltage support service, black start service. So grid investment deferral. So those all advantages are being offered to the transmission and distribution system. Then regulators. So basically, we need to have clear regulations, clear policies and rules for the adoption of these storage systems. So that brings us to the Q&A session. We'll discuss some multiple choice questions here. So first is which of the following is not a mechanical energy storage system? Compressed air, gravity, pumped hydro, or latent? You can unmute, you can type in the chat box. Okay, Rajesh says latent. And what about Akhtar, sir? Can you say what form of energy storage is latent? It is thermal, I think, right? So latent is the correct answer. Next, which of the following combination of energy storage technologies are not feasible for hybrid energy storage system? So hybrid energy system we did not discuss. In hybrid energy storage system, what we do, so there we discuss no that the storage cannot have both high power and high density feature. So what we combine is one energy storage technology with high power density with another energy storage technology which has high energy density to form a hybrid energy storage system having both the features. So you need to look that which of the following combination is a combination of a high power density technology with a high energy density technology. Lithium ion and sodium sulfur batteries. Um, no. So lithium ion is high energy and sodium sulfur is high power. So this is a hybrid energy storage system. Any other option you feel? Yes, A is also a hybrid. So supercapacitor is high power, battery is high energy. In C also vanadium flow is high power, lithium is high energy. Basically all of these are hybrid energy storage systems. So none of this is the correct answer. Then match the type of energy storage. First is chemical. So which of this one, two, three, four is chemical type of energy storage? Chemical is battery. So chemical, actually, battery is not purely chemical. So can you rethink? Sorry, fuel cell, huh? Yes, that's right. So chemical is fuel cell. What about mechanical? Yes, flywheel. So mechanical is flywheel. Then electrochemical. Yes, battery is electrochemical and electromagnetic. Then we are left out with superconducting magnetic energy storage. Okay, next is which of the following storage type has high energy density? So I think that is very repetitive. Yes, lithium ion. We discussed due to this, it is being actively used in EVs and portable electronic devices. Then next question is a 12-volt battery with capacity of 500 ampere hour is at 80% SOC. Find the DOD, depth of discharge. DOD, depth of discharge, is nothing but 1 minus state of charge. So if state of charge is 80%, so depth of discharge will be 20%. The next question is a 12-volt battery with capacity of 500 ampere hour is at 80% SOC. Calculate the energy stored. So basically capacity is 500 ampere hour, which means your 100% SOC means the capacity is 500 ampere hour. So currently the SOC is 80%. So the energy now will be 400 ampere hour. Then which type of problem is a distribution network planning problem? Linear programming, mixed integer linear programming, mixed integer nonlinear programming, nonlinear programming. So MINLP. Can you say why it is a mixed integer nonlinear programming type? Whenever we say a planning problem, that means it can either be generation expansion planning, or it can be transmission line expansion planning, or it can be a distribution expansion planning problem. So a planning problem basically means we consider the various decisions such as installation of various new components, such as installation of generators in generation expansion planning, or installation of transmission lines in transmission line expansion planning, or installation of distribution lines or substations, breakers, and rest all things. So, so their decisions here we consider is whether to install it or not. So as we saw in the battery optimal sizing and setting problem, so that will involve the binary variables. So these decisions binary variables means binary 0 or 1 it can take. So 0 means there will be no installation. 1 means there will be installation. So we need binary variables for such problems. So hence we uh, mixed integer basically means the presence of integer or binary variables. That means we ruled out linear programming and nonlinear programming. Next thing that we see, we have to see whether it will be a linear programming or a nonlinear programming. So linear or nonlinear is basically defined whether the constraints and the objective that you have used, whether they have any nonlinearity or not. So various sources of nonlinearity are basically like your multiplication of two variables. So multiplication of variables, or there may be involvement of sine, cosine, that is trigonometric terms, or exponential terms. So those all again introduce nonlinearity. So these are some sources of nonlinearity in the system. Now coming to the distribution network planning problem. So we know that the power flow through the lines that we see is represented by something like that: Vi, Vj, Gij, cos delta I minus delta j minus theta ik. So here we are having both multiplication of variables, and that is Vi, Vj, two variables are being multiplied. Then there is also cos terms. That means these equations are nonlinear. So that then brings us that our problem is a nonlinear programming with binary variables. That's why we are handling a mixed integer nonlinear type of problem here. Next is select the advantage of mathematical programming approach. Low computation burden, global optimal, short convergence, simple formulation. Low computation burden, no, actually, for higher systems, it will be having significant computational burden. So, as I said, it is having computational burden and convergence time also it will take time because computational burden is there means again only time will be high. Then global optimal solution. So let us see what is meaning by global optimal solution and local optimal solution. So in case of your linear programming type, that means your constraints and objective are all linear. So in that case, you have one solution which is your global. But in case of your nonlinear, so both for LP and MILP, mixed integer linear programming, we have one solution which so your objective function will be something like this. Sorry, so if it is a minimization problem, so it will be something like this. Let's say, and this is your global optimal solution because your function is minimum at this point. But in case of nonlinear programming or MI and LP type problems, what happens is your objective function will vary like this maybe. So you can see there are multiple minimum solutions here. This is also minimum, this is also minimum, this is also minimum. So all these are local optimal solutions, but there is one global optimal that this is your global optimal solution. These are your local optimal solution. So what happens in case of nonlinear programming is if you go for methods such as heuristic, so what they will do is they may be trapped in the local optimal solutions. But in classical mathematical based approach, they will be guaranteeing you the global optimal solution. And these machine learning techniques, they even cannot sometimes guarantee the optimality for linear type systems. So hence, for mathematical programming approach, the biggest advantage that we get is global optimal solution. But due to this, they have complex formulation and hence the computational burden is higher and convergence time is also high. The next question is the indication of the SOC of a battery is best given by which of the following? Yes, anyone else? So the SOC you can not obviously see by the temperature or the color, the level of electrolyte because electrolyte is nothing but a liquid kind of solution. So level of electrolyte is basically the volume of solution. So looking at that also you can't say. So basically the specific gravity of the electrolyte. The next question is data based. The first commercial lithium-ion battery was released by Sony in which year? Yes, it is 1991. Which of the following matches is false? This we saw. This was high energy. Flywheel is high power density. So this is hybrid energy. Biofuel is chemical. Lead acid, similar to lithium ion, is electrochemical. Pumped hydro, here only one storage technology is here. Pumped hydro is high energy density. So it is not a hybrid energy storage system. So this is the correct answer. Then next is which storage technology has a very good usable capacity? So usable capacity here implies basically high energy density only. And this we have seen repetitively. This is lithium ion. Which storage capacity, what is the storage capacity of the largest solar power battery by Florida Power and Light Company? Yes, it is database, it is 409 megawatt. Energy storage tender activity increased by what percentage in 2021? Again, it is data based, it is 41%. Then, which is not an active cell balancing method. Cell to cell, overcharge, cell bypass, pack to pack. Yes, overcharge is passive balancing. Then suppose the objective function of an optimization problem is convex. then which of the following is true regarding the overall optimization problem? So it is being said that the objective function is convex. Now, depending upon the constraints, we have to comment whether it is a convex or non-convex problem. So, whenever there is linear problem means it is always convex. So, second one is correct. Now, whenever the presence of non-linearity is there, so it does not always imply non-convexity. So you may face some non-linearities such as the quadratic means multiplication of two similar variables, quadratic terms, and then some second order cone type of also we have think. So this is a non-linearity, but still it does not make the problem non-convex. So sometimes it can be convex, it can be non-convex. So hence, nonlinear constraints may result in non-convex optimization problems. Next is why battery management system is required. Hmm. Yes, we have seen it helps in increasing the battery pack efficiency because it helps in cell balancing with the help of cell balancing, optimal usage of battery, then by thermal control and monitoring. It also reduces the prematurity or degradation of the battery. Hence, all of the above is correct. So this brings us to the end of the question, multiple choice question. So if you have any other doubt, you can ask, we can address them. If not, then we can close the session for today and we'll meet in the next session discussion. Thank you. Thank you for joining. So then I will end today's session. We will meet next on next Saturday for the next week discussion.